Hello everyone, I'm Kenneth, and I'm a 9-year alum, and I go to UCSD as an aerospace engineering major. Today I'll be talking about solid mechanics and material science. So the 4 questions I want to answer is how to pick the correct material, to pick the right bolt size, how big of a hole we should use, and what material we should use, and how thick should the material be. So before I get into that, I want to talk about some tips for this season. If you noticed here, a lot of people have asked me about the relationship between FRC's Ultimate Ascent of 2013 and this game. Now, a disclaimer, I don't want to really be giving you what to say, basically saying you guys should do this, or and I don't really know how the onion rings feel like. I just know they're soft and foamy. But I want to say that if I was to say this is the 2013 Frisbee game, a lot of teams, what they did is they created a U shape. And if you look at this YouTube video, they basically, this one, yeah, if they could look at this YouTube video, the Frisbee travels in a U. So essentially what we want to do is we want to transfer as much energy as possible from the wheel to the shooter. From this year, in 2013, a lot of teams, what they did incorrectly was they only had one point of contact. So possibly many times the Frisbee would only touch this wheel maybe like for an instantaneous second, and you don't want that. You want to have there's the physics behind it, but you want to either have a U, or in another case, I think there is a linear way of doing it. So I think in this example right now, it travels in a linear way, meaning it has multiple wheels lined up as kind of like a belt, or kind of like, and it shoots out the first piece. This might be more practical for FTC purposes. So if you look in the video right now, these belts can be obtained at McMaster, and what they do is they basically it travels straight and shoots out the first piece. So yeah, so just some tips from the 2013 year that I can give you. And yeah, remember, I don't want to kind of be saying, hey, use this for a design. I just want to kind of give you some tips. Other possible ideas, so as I said earlier, this straight kind of shooter. So without the U, it has multiple wheels as you look in 1592's robot. And also on the bottom right, I have another kind of U shooter. I'll just call it that. And then on the top, we have a catapult. I'm just giving you random ideas that you guys can possibly go off of. But yeah, explore different ideas. This is going to be an interesting game, shooting those onion rings. And yeah, I don't really know how the onion rings feel like, but these are some possible ideas. If I was to say the onion rings were kind of like frisbees, yeah. So now going to constraints. So this year you guys have more constraints than usual, because you have COVID-19, and because because of mainly COVID-19. And so first thing, size. Can you really make an FRC style shooter? And how accessible are the materials to you during COVID-19? So as I said, some materials in those videos you can get it at McMaster, you can get it at Animart, you can get them at maybe some probably maybe some at Harbor Freight, some at Home Depot, Lowe's. But you want to see how accessible are these materials. These are constraints you should really consider about. And another thing you should be concerned about is probably defense. I haven't really analyzed the game, but I've heard like there's a lot more interaction between robots, and there's probably more defense that can come that could arise. So think about it. So the entire purpose of this material science workshop and solid mechanics workshop is to kind of allow you to design a more kind of reliable robot. So if there is more like interaction between robots, such as like FRC style, like you guys are bumping around, um, I hope you guys can actually do the calculations and kind of find what material should I use, how big of a bolt should I use, what should I do with my design, how can I design a more effective robot. Yeah, so essentially, I'm sorry if so sorry guys, my recording was off, so let me continue. Engineering design. So what we're doing here is basically all about engineering design. It's we are defining a problem, and then we're creating a solution. But in between, we have to think about different things that will factor into the engineering design, such as how do I make how to pick the right material. What should my prototype be like? How do I create my design? So this is what I want to mainly talk about. It's more about the design. So going back to the topic's goals, how to pick the correct material, how to pick the right bolt size, how big of a hole should we use, how thick should this material be. This is things you guys should really be considering more. And I don't want this presentation to be kind of more of a problem session. I don't want to go through um, these 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 topics. I don't want to go through it with just showing you problems. I'd rather be going through more of a theoretical perspective. So if you look at this next slide, this is just a common problem. So like an L bracket with two bolts going across of it, and then we have a bolt and a nut. So this is a common problem. This is kind of something I want to stay away from today, and it's really easy, and you can probably find these problems online, and you can look them up. So yeah, so really simple problems and stuff I want to go over. I want to go over the theoretical stuff. So yeah, I want to go over theoretical. I don't want to just give you these formulas. I want to these problems are easily found. So I hope you guys are ready for some fun. So let's get started. I do regret if this kind of ends up sounding like an AP Physics course. Lloyd, who's our moderator here, says we did a practice session and it does sound like an AP Physics course. So, but I tried making it more fun. I added some memes and fun stuff. So this is important. So let's get started. You probably have interacted with compression and tension forces. They are really, you probably do it in your AP Physics courses, and you guys do like free body diagrams and all that stuff. But compression force is a force that pushes materials together, while a tension force is a force that pulls materials apart. A really simple concept you guys can go over. If you can look at it, it's like this picture of a guy being squashed versus like this rope of two people pulling together. So yeah, so it's a positive axial force that indicates tension. You guys can worry about this in the future. So moving on to the next topic, and sorry if the recording has the voice a bit off. Moving on to the next topic, a shear force. So a shear force is a force that you probably haven't really interacted with. It is basically, if you look at this picture of the bolts, it is a force parallel to the material cross-section. What does this mean? Look at this picture on the right-hand side. It has a bolt and then two plates. So essentially, say those two plates are pulling in opposite directions. That is creating a shear force applied onto the bolt. So in your regular AP Physics course, you probably haven't really gone through anything related to shear force, but it's really important for robotics, especially because we use bolts. So if you look at this diagram, it's not shear force isn't that difficult of a topic to understand. And if you look at the diagram on the bottom, we have let's say a C channel or a U channel, and then we have a plate, and this is and essentially it's sandwiched between, and we have basically we can say like maybe three forces applied onto this bolt, and they're all shear forces. So robotics with shear forces, you'll probably learn a lot about it in your in college. So the five forces that are really important is compression, tension, shear, torsion, and bending. Now, torsion and bending you'll learn about in the future, so don't worry about those. But I would say in your job interviews, you really want to consider them. Moment. So a moment isn't a type of force. It's a tendency of a force to cause a rotation of a body around an axis. So if moment is just simply a force times distance, and you guys shouldn't have to. You guys should probably know this from your high school physics course or just in general. So let's get on to the more important topic: stress versus strain. So it's not the stress of this sleeping on the table. This is a tensile strength test. So essentially we're using a dog bone and we're pulling that dog bone apart. Let me see if I have a... So basically if we want to use the rubber band analogy, if I had a rubber band and I stretched it out, it would experience stress and strain. So essentially what I'm asking is, what is stress? So stress is a force over a cross-sectional area, so F over A. And if you look at this cylinder, it's just that area, that circle, yeah, and then you pull a force. So that area of a circle is your cross-sectional area. So it's force over area. And you would typically correspond compression or tension with sigma, and then shear with a tau. So again, to simply put it, um, stress is force over area. And moving on to strain. So strain is elongation over original length. So how much of a change is there over the original length? So strain is the response of an object to stress. So stress is the amount of deformation. Strain is the amount of deformation of the applied force divided by the initial length of the material. Yeah, so it is again over elongation over original length, as you can see in this picture. And then, sorry, there's a bit of a lag. So strain is, again, to say it again, it's elongation over original length. So moving on, we have the stress versus strain curve. We have the plastic region and the elastic region. So let me first show you this stress strain curve. First of all, we have this elastic region. What the elastic region means is it means when you stretch out a material and then you release it, um, the, the material returns to its original shape. Meanwhile, in the plastic region, we have permanent deformation. What does that mean? It means that, for example, if I took a rubber band and I stretched it out, and then I released that rubber band, keeping in mind that when I stretch a rubber band, I probably have to stretch it enough in order for plastic deformation. But when I stretch it and I release it, it seems deformed. It doesn't seem like it returned to its original circle-y shape. So that's essentially the difference between the elastic region and the plastic region. The elastic region, it returns back to its original shape. You stretch it out, you release it, it returns back to its oval or circle. And meanwhile, the plastic region, you stretch it out, release it, it deformed. Yeah. So moving on, the stress strain curve. This is a more detailed analysis. So on the first, we have a linear part of the graph. As said, the stress strain curve, they're proportional to each other on this linear portion. And you have Young's modulus. So if you, actually, let me describe the video first. If you look at this video, you can see, if I can get it, you can see that the material is being stretched. And Young's modulus is essentially the slope of this graph. Every material has a different slope. And I'll explain more about Young's modulus in a second. At the end of this elastic region, we have the yield strength. So the yield strength is the location where it stops being elastic and becomes plastic. And at the top we have the ultimate strength. I'll explain more about it, but that's the maximum stress the material can withstand before fracture. So elasticity. Elasticity is the linear portion. Most people see it as a linear portion. However, it might be slightly curved, so we use the secant modulus or the tangent modulus in this case. Yeah, so really simple and really straightforward to go with. And then you probably won't have to worry about that. But going back to a linear portion, so modulus elasticity, the slope, that's the most important part. Every material has a different slope, to say. So for example, if you look at this graph, the modulus elasticity is essentially a measure of stiffness, the ability of a material to resist stretching when loaded. And every material has a different property. So let's say looking at aluminum, it has 69 gigapascals. That is the Young's modulus of it. And then it has a 0.33 Poisson's ratio. I'll explain more about Poisson's ratio shortly. So yeah, every material has a different slope to say, has a different modulus elasticity, and this is the Young's modulus is really important when doing calculations. So, sorry though, my Wi-Fi disconnected, so let me start all over again. Let me go. Let's see. Give me a second. Okay, so modulus of elasticity. So a measure of stiffness, the ability of a material to resist stretching when loaded. Um, as I said earlier, and I don't know if you guys were able to hear it. So every material has a different Young's modulus or modulus of elasticity. Um, with third saying that essentially, if we go back to the stress versus strain curve, this is the linear portion. Remember that, and the steeper it is, the higher the slope, obviously. And going to the next part, at the end of the yield, elastic region, we have the yield strength. And let's see next. Okay, yield strength. End of the elastic region and beginning of the plastic deformation, aka permanent deformation. Okay, so yield strength, very easy to find, but I won't really go over it. It's basically we use the 2% rule. So this is it is when you can find the point where it starts to plastically deform, meaning permanent deformation. Yeah, so you guys can go over this yourself in the future. So ultimate strength. This is the maximum stress that a material can withstand while being stretched or pulled before breaking. So if you elongate, if you stretch the material further, it will fracture. So essentially, when we don't want to really get all the way up to the ultimate strength, because after that it will fracture. So fracture strength, basically, its name defines itself. It's location where it fractures. So Poisson's ratio, I talked about it earlier in the chart. So Poisson's ratio is measure of the Poisson's effect, the phenomenon in which a material tends to expand perpendicular to the direction of compression or tension. So look at this green box. So pretend I pulled this material. So the green box is the original. I pulled it apart. See if you can see it gets skinnier. Like it gets less wide, but it also gets longer in the x direction. According if you look at the XYZ graph here, so it gets longer, but it also gets skinnier or thinner. Let's see. Okay, so basically the Poisson's ratio is, if you look at this, the solid lines are the original ones, and then let's say I stretched out this in tension. I placed this in tension. I stretched it out so it gets, so you can see that it gets narrower, but it also gets longer. This is what happens with Poisson's ratio. Meanwhile, in compression, I compress it. So solid line as original, I compress it. It gets fatter, it gets wider, but it also gets shorter. So this is essentially what Poisson's ratio is saying. And if you look at this diagram, this is the rubber band. I'm pulling the rubber band, so the width decreases, and then it gets longer. This is a good diagram. This is a good video diagram. So I pull it, it gets narrower, and but it elongates. So brittle versus ductile. Okay, so in material science, people in the regular people we always get confused between ductility, resilience, and toughness, and strength, and all that. They would use these terms interchangeably, but in material science, each term has its own actual definition. So ductile materials stretch a lot before breaking, while brittle materials deform very little before breaking. Say I was having glass now, and I took a hammer and smashed the glass. That would be a very brittle material. So brittle materials deform very little before breaking. So they don't get to deform, so you can't really stretch out glass. When you hit it, it shatters. If you look at this, it has a very short deformation. So if you look at the string part, it's really short before it breaks. While a ductile material, it's basically, look at the area too. You can stretch it out a lot before it breaks. Yeah. So ductile material, you can stretch it out before it breaks, and brittle material, very little strain before it fractures. So moving on. These properties, these terms define the material's behavior. So that's important to remember. So yeah. So glass is a very brittle material, but also another type of brittle material is carbon fiber. So you probably are really fascinated by carbon fiber. Carbon fiber is extremely brittle but chemically strong, meaning it kind of reacts like glass, but it's really strong. So we build carbon fiber in laminates. So what does laminate mean? It means layer by layer, and we have different degrees. These matrices look really difficult right now, but they're really simple. When you look into it, it's just you orientate the layers in different angles. And carbon fiber, as I said, it's chemically strong, meaning degrades. When it degrades, it's better at resisting, for example, low temperatures or high temperatures. It's better at resisting those. Very similar to glass, which is why probably cars use glass for the windows. Yeah. So my apologies for a slight lag. Yeah. So essentially, these calculations, as I said, very simple to do. So let me move on to the next slide. Okay, so I won't really talk about ductility, resilience, and toughness. It'd take too much time. Also, elastic recovery after plastic deformation. You guys can look over it. It's essentially metals can recover their original shape after being stretched to a certain limit determined by the metal's yield strength. So yeah, essentially this graph kind of tells itself. I guess really simple, but I don't really have too much time to talk about it, so I'll move on. So how does this apply to FRC and FTC? One team at LA, the LA North Regional, they used mechanism wheels. So, and they had to go over bumps. And as I watched, I always saw that those mechanism wheels would keep on breaking. And what I'm saying is, you have to, when you're designing a robot, even mechanism wheels that were bought, we want to really consider how that material will behave. So yeah, so in FRC, this robot on the bottom here had a really cool arm. I think they're from Israel. Yeah, so essentially, I'm trying to say is that even though you're designing, sorry as a cutoff. So even if you purchase these items from a store, you want to consider how you guys are using these items. For example, the wheels, what applications or what will the wheels have to endure. So I want to go into more of, for example, have the chassis. If there's probably more defenses here. So what if I had FRC style defense and they're pushing you around? How would these bolts withstand this? And you want to kind of apply and think about the safety factor, the margin of safety. How should I design this material to be? How should I design this component to be effective and reliable at the same time? That's what we really need to consider about. So in FRC, we use aluminum 6061. I'm using FRC because I'm more of an FRC person, and I had this PowerPoint design for FRC. So aluminum 6061, the tube, we commonly use 6061, as you see in this picture. So 6061, it's really cheap. It's $3.64 per 1 foot of tube, per foot. And I know what material, so now I can use internet, and I can find the properties for the material. For example, it has young modules of 68.9 gigapascals, tensile strength, elongation at the break, so 12 to 25%, and Poisson's ratio 0.33. So essentially, you guys can. What I'm saying here is, find out what material you're using, and go online and search up for these properties. And then afterwards, you can apply them to your calculations, because you essentially, all formulas are almost always plug and chug, almost. But you don't know what properties you have. That's, I think, might be the harder part, is finding the properties, finding the materials. How will something react? So especially finding Young's modulus. That is really important to calculations. So aluminum 7005, that FTC. Tetrix, I went on their website and I found that they use aluminum 7005, and this has a tensile strength of 350 megapascals. What does this mean? 350 megapascals, if I go back, this has a higher tensile strength than 6061, which has 290. So yeah, that means it has a higher one, it's stronger. Has a higher strength. So these facts, these properties can easily be found online, and I just found this off Wikipedia. So what I'm saying is you want to look up which materials you're using. You want to be careful of what materials you're using. Um, this is really important. So here on the top, for example, I said Baltic birch. Um, how what So I noticed a lot of teams use laser cut wood. Um, some teams do, and I would recommend Baltic birch first of all. It's kind of like the carbon fiber of woods, if you want to think about it. It's very strong, um, but also to consider about it, wood in general. When I use wood, what would happen for a certain component? What if I used it from a sponsorship thing? Uh, how about aluminum? If I used aluminum, how much heavier would it be? How would it be stronger? So these are the properties you want to be looking up. You want to be analyzing. You want to be the thickness too. You want to think, oh hey, what is the minimum amount of thickness? And later I'll kind of go into more of how to pick the correct thickness with the safety factor. Um, so yeah, the good thing about FTC, you're limited to what you can use. It's more strict than FRC. So yeah, let me go move on. Sorry. Okay, so Fastenal. So Fastenal is a very good website for you to buy bulk items, especially bolts and screws and all that whatnot. Um, but what I'm saying here is again, on Fastenal's website, you can always look at the material properties. For example, the grade, the finish, the drive size. They sell almost everything you would need for a very more affordable price. And um, and let me see. Nah, never mind. Actually, we can get the thread length. We can get the drive size. We can get all this stuff. So let me move on. Let's see. Um, with all these things, all these numbers, all these properties, we can use SolidWorks to do our force calculations. That might be the harder part in this. Most of you guys probably CAD or robot, and you probably make your or use any other software to do it. And most of them probably will have a digital simulation. So simulate your forces, find your forces. But the most important thing to think about is your safety factor. Don't really worry about these equations. It's essentially just safety factor times the load to get your new higher load. And safety factor is basically based on why we need it is we have load variations, material variations, fabrication variations. And it's used to establish the safety and complete reliability of the structure. It's used to lower the chance of failure. Because we have too many variables, we need to consider all these variables. We need to consider what would happen. Load variations. We can't really find our load in our robot because we don't really know what it is. The folks at, for example, at Boeing, they probably have everything calculated. So give me a second. Hello. So I apologize for the next maybe like 6 minutes of content. My Wi-Fi kept cutting out, so I'm kind of improvising on this recording. So safety factor. Going back to safety factor, it's basically based on material variations, fabrication variations, load variations. We don't have absolute control of these variables, so we use a safety factor to lower the chance of failure. And we want to establish the safety and complete reliability of the structure. That's essentially why we're using a safety factor. We want to improve the reliability of a structure. So let's see. Yeah, fabrication variations. When I talk about that, what do I mean when I talk about that? So that means when I'm making something, even though I'm using probably a CNC mill, your fabrication might be slightly different. It might be slightly off. And also load variations. That one is in robotics most important because a lot of times when you design something, you don't really know how much load there is. When I pick up a ball, how much load that arm is really going through. Material variations. Even though this might not be as bad because you're mainly purchasing things off the shelf, there are still variations in materials. So So yeah, considering safety factor, it's basically there's a safety factor, maybe like 1.5 times your load, so you get a higher load, and you would use that. So I borrowed this from Boeing. Uh, in with Boeing, they use a safety factor of 1.1 for unmanned critical weight critical aircraft, or they could use typically they would go for 1.5 for manned and inspected, but they'd also recommend a safety factor 2. Well, Boeing uses these safety factors because they're conservative with their value. They use conservative safety factors because of all the calculations they do. They everything's really precise. They do all these calculations, and everything is well planned out, and that's why Boeing is able to use such low numbers. Well, here's a video from the 777 wing test, and let me scroll through this. And essentially, what they're doing is they're trying to bend the wing as much as possible. Um, and they're trying to find at what safety factor would or what percentage will the wing break. So if you look at this video, I think this guy on the top right is the father of the 747, trying to get his reaction. But if you look at the wing snap, so in this video it tells you that the wing snaps 154%, so 1.54. So you can be well assured that your plane won't be breaking anytime soon with the wing snapping. But like yeah, so in FRC, the question is, what do we use? Now, well, or FTC too. In Chief Delphi, in dynamic cases, recommends a safety factor of 4.0. So why 4.0 versus 1.5? Well, Boeing calculates all their numbers. In our situation, most times we haven't really considered all these calculations, all these forces, all these variations that might be happening to our robot. So yes, so we would have to apply a safety factor of 4. Well, in controlled situations, we can use a safety factor of 2. And um, safety factor, why is this important? We don't want our robot, say we're going on Einstein's, we don't want our robot to be breaking, as I said before, I think. We don't want our components to start failing. We want higher reliability. So moving on with fatigue. Fatigue is a phenomenon most engineers don't really know about still, because we haven't had the time, we haven't had enough experimentation, or that's what I believe. So look at the 787. Boeing is constantly still testing, loading and unloading this aircraft wing and this entire aircraft structure, like to simulate flight, because they don't really know about fatigue, and they want this aircraft to they want to see what happens to this aircraft before it actually really happens. So yeah, if you want to, I think this is in Everett, Washington. So I think this is actually really cool. We don't know much about fatigue, but this is a real life simulation. So we want to find the breaking point of this aircraft when fatigue will actually hit this aircraft before it actually does for a real aircraft. So yeah. Moving on, I think. So moving on, we have our splice plate. So this is kind of like the general way of testing it. We have 2 plates and then bolts. So I won't really go into the details of this calculation, but essentially we can calculate everything with the safety factor. For example, we are given the normal stress, and we have to find the load, how much load is applied. So for example, it applies 3,100 psi, and then you have safety factors given as 3.5, and then so you would have 885.714 psi in allowable normal stress. Then we would multiply it by our area, which would give us our allowable load. Also, I've also released some example problems that you guys can be going through, so you guys can be going over it. And I don't have much time today to explain this, but you guys can look over the PowerPoint, right? All this information that will be valuable. But overall, thank you for attending this workshop.